This is one of the most important fields or subfields of linear algebra. Most practical ones, like at least half of the applications dependent on that theory, okay, on these singular values and not even eigenvalues. And practically you already saw them before. I haven't named them. I kind of hinted that we will be talking about them, but I didn't show them. So it's called SVD, singular value decomposition. And the idea is to generalize eigenvalues, and you already hopefully believe me that they are important, like $25 billion important, okay? And we want to generalize it to non-square matrices now. Not symmetrical, non-square, just generic rectangular table of numbers, whatever the table is, all right? We also want to produce additional decomposition of matrices where we'll have simple geometric interpretation for each part of that decomposition, which is, again, extremely important because if you know how to interpret that, you can understand what parts are important in the decomposition and what parts are not important in the decomposition. And it's, for interpretability, it's very important. Okay, this is a very interesting phrase that I like. That's Swiss Army knife and Rolls-Royce of compositions. It's really used almost everywhere, and for some reason, nobody learns it in undergrad degree. I don't know why. This is not much more difficult than eigenvalues and eigenvectors, but you spend probably like 3-4 lectures on that part and nothing on that part. I don't know why. All data analysis is based on that, at least, okay? All machine learning algorithms, least squares, solving different system of equations with too many variables, too small number of variables, all dependent on that pseudo inverse and so on and so on. All of that SVD, okay? All right, so here's where it comes from. This is actually very unexpected to me, at least, idea that any matrix, and if you remember matrix, you can think about that as operator on a particular vector. So if you multiply matrix by a vector, it rotates the vector, scales the vector, shears the vector in some weird ways. And different matrices will do that in very different way. If matrices are not rectangular, you're also changing the number of dimensions of the output vector, right? So if you have like m by n, and you multiply that n by 1, you get m by 1 from vector of n by 1. So you're changing the number of dimensions, depends if it is like thick matrix or thin matrix, rectangular, right? So you're adding more dimensions or you're removing some of the dimensions from your original n-dimensional vector when you multiply it by matrix. So it's not only kind of rotating it and squeezing it and inverting it and doing all of that stuff, but it also kind of cuts some of the dimensions if you multiply by rectangular matrix, or adds more dimensions, depends by the dimensions of the matrix, all right? So this idea that any multiplication by any kind of matrix could be represented as product of 3 matrices. One is rotation, one is scaling, which is practically a diagonal matrix, and another rotation. This is kind of unexpected, right? It sounds weird, but this theorem states that you actually can always do that. And I need to say maybe additional thing, I like details. So this is not 100% true, okay? It's not only rotation, but also flipping. You can flip upside down, left, right, flipping. So it's additional action, which is not exactly rotation. You cannot like rotate by flipping left, right, for example, right? You cannot find rotation which will flip the matrix, flip the result upside down, like vector upside down. You cannot do that, right, with just rotation of the vector. So you can get negative number of the vector as well. And it's logical because you can always multiply that thing by minus something, and then your vector will have opposite direction, which is not rotation of that vector, but just flipping the vector in opposite direction, right? So it's kind of rotation, but mirror reflection also possible. So the point is that you can do any kind of scaling, shearing, and reflections with these three operations, okay? And these are like you doing that in order, one after another. And if you remember, rotation matrices are unitary or orthogonal matrices, which are very nice because their property is that that matrix transpose times its own will be always I, which means their transpose is their own inverse. Very nice property of these matrices, okay? So rotation matrices are very nice. And you can write any matrix as multiplication of these three. Isn't that great? This is what SVD is, like how to write it as rotation times diagonal matrix times rotation. And by diagonal matrix, I'm not always saying that this is square diagonal matrix. It could be also like very long diagonal matrix where you have diagonal elements and everything else just zeros here or zeros there. It's still diagonal, but not rectangular diagonal in a sense, because we defined diagonal as square matrix, but it doesn't have to be really. You can pad it with zeros anywhere. Okay, so far, this is what I mean by diagonal in this lecture. Any questions? And you have tons of applications. We've seen that already in PCA. So PCA, when you're doing eigenvalues of the V transpose V matrix, these are singular values of the original matrix, okay? So if you're taking matrix transpose matrix and making eigenvalues of that matrix, these eigenvalues are singular values of the V matrix. This is what it is, okay? We will see that a little bit later. But technically you saw that already, okay? So it's just kind of different representation of the same thing and becomes a little bit more interesting later. You use that for noise removal, you use it for ranking by data, ranking by importance. As PCA, you use it in regression models for function fit in least squares, all the series. That you have tons of different applications here. And here is how it works, okay, in practice. So any matrix, and this could be complex or real matrix, it doesn't matter, M by N, rectangular matrix. It could be square matrix, but doesn't have to be. Just any matrix could be decomposed as U matrix times sigma matrix times V matrix. And again, this matrix will be diagonal matrix, and these two matrices will be orthogonal matrices or unitary matrices in complex sense. So unitary means that U to the H, U equals I. This is the only difference from orthogonal, okay? So orthogonal typically associated with real matrices. So orthogonal is like U transpose U equals I. But in complex matrices, we're doing Hermitian transpose instead of regular transpose, conjugate transpose, okay? So this is why we call them different name. We call it unitary, not orthogonal. But again, think about H as transpose always. It's like transposing the matrix. And most of the times we will be working with real matrices, so it doesn't matter really if it is H or T, okay? Same thing, orthogonal matrices. So both U and V are orthogonal. This is what we know about these matrices. Now, sigma will have only diagonal matrix, it's diagonal matrix, so only diagonal values. And this will be our singular values of that matrix, original matrix A, okay? Now, since this matrix having only real values, and as you can see from here, it will be only eigenvalues of that type of matrices, which are by definition symmetrical. Why are they symmetrical? Why do you think like U transpose U is always symmetrical and V transpose V is always symmetrical? Or any other matrix transpose with that same matrix, like A transpose A is always symmetrical. Why is that? This is very simple, actually. So my claim is A transpose A is symmetrical. This is the claim. Very simple to show. What is symmetrical? It means that transpose of that matrix equals to matrix itself. But what is transpose of that thing? Remember, transpose of multiplication is switching the order of matrices and doing each one of them transpose. We'll get A transpose from that one, A transpose transpose, which is the original matrix. So this transpose equals the matrix itself, which means it is symmetrical, right? And for symmetrical matrices, as I mentioned, we'll always have real eigenvalues, which you can sort in particular order, and this order will be like that. Sigma 1 will be the biggest one, and sigma n will be the smallest one, okay? Some of them might be 0 as well, all right? So some of this I'm still in the previous lecture. So some of the singular values could be 0, all right? And we care only about the ones which are not 0. So these are singular values, and you compute them as eigenvalues of the matrix A, Hermitian transpose A, square root of that. All right? This is how you compute those singular values. So they have very close relation to the original eigenvalues and eigenvectors and all of that stuff. But it's just defined like that. And we will see why this connection exists, all right? Same idea, same geometry, same everything practically. Singular values tell you how much you stretch particular space and particular dimensions just for those matrices instead of original A matrix. Because A matrix is not square anymore, but this matrix is, okay? If you're doing A transpose A, it's symmetrical and square, regardless of what A you started with, all right? So for that matrix, you can compute eigenvalues and eigenvectors and so on. And the singular values will tell you how much you stretch in each direction, that kind of thing. And this is true. Why? Because you can multiply by V from the right, by V transpose from the right, actually, both sides, and you will get the original definition. Because V transpose will be just I. So on the left, you will have A equals U sigma V transpose, which is also V inverse in that case. It's like eigen decomposition in a sense, but with two matrices, U and V, instead of single matrix, which was a T matrix with eigenvectors of the original matrix. All right? Any questions on that? So this is how it is defined. Haven't showed anything important yet. It's just definition of what singular values are. In MATLAB, it's also a single line of code. Command SVD of matrix A will give you U, S, and V. And S is at sigma. Right. Any questions on that? Yes.
Sigma matrix, it could be like every diagonal is all zeros.
It could be zeros, yes. Or it could be rectangular matrix of any kind. Technically. It could be square, it could be rectangular, it could be depends on the original matrix. Because if you're looking on that thing, it could be M by N, all right? And we will look at the compact representations and thin representations of singular value decomposition in a minute, where we will shorten and remove all of the zeros because you don't really need them to represent the same matrix A. You can have much shorter and simpler representation. And this is also the beauty of that singular value decomposition, because you have so many zeros there that you can completely ignore them and remove parts of the matrices and make them much smaller. And for storing information, for compression, image compression, for example, you can use it, or for any other compression of data, you can use it as well, okay? Because it's decomposing it and having many, many different zeros in different places. All right, so this is explicit writing of the SVD decomposition to three different matrices. And again, I'm not explaining right now how you compute them. We will get to that later, probably next time. But here I am just showing you explicitly how it could look like, all right? So first of all, you will have all kinds of vectors, U1, U2, U3 in that matrix, and you will have M of them, because again, you have M by N here, so this matrix needs to be M by M. So each vector is like length M, and you have M of them in general, all right? Now, they will be multiplied by the diagonal matrix, where you have sigma values sitting on the main diagonal, and you will have only R of them, and R is rank of that matrix, original matrix, okay? So if you have matrix like 100 by 2, you cannot have more than 2 singular values which are not 0, because the rank is just 2, all right? So this matrix will be big, but all of them, almost all of them will be 0. So you'll have only a few of them, everything else will be on the right, all of the zeros on the bottom, everything zeros, okay? And you cut it anywhere, because if you multiply that vector by like vector of zeros, nothing happens. It's not changing anything, right? It's just nothing. And same thing here, you will have n rows which are transposed columns of matrix V. Okay, this is how I write it. And again, transposed or Hermitian transposed, doesn't matter, some sort of transpose. For simplicity, I just call all of that transpose. So U will be called matrix of left singular vectors. This is that matrix. And V will be called matrix of right singular vectors. So instead of, we had only one set of eigenvalues, but singular would be left and right for different matrices. And columns of U and V are already in the order of importance, which means farther you go with the vectors, they correspond to smaller and smaller sigma values. And eventually they correspond to 0 sigma values, which means, what does it mean geometrically if you have sigma equals to 0?
No stretch. It's point.
No stretch. It's not only no stretch. You squeezing it to 0, all of it. You squeezing the entire dimension to 0. You don't have the dimension at all. So this dimension is practically 0. When in your original matrix it's not 0, it means that you can represent the dimension with linear combination of other domains, other dimensions, okay? It's almost like we thought about bases, if you remember when we discussed bases from the matrices, right? If you have more than n vectors in the basis, obviously they will be dependent. So you cannot have bases more than n vectors if you have like Rn or something, right? So you need to have n vectors in that basis. Otherwise, if you have too many of them, they definitely will be linearly dependent, too many of them, all right? Same thing here. So you'll have only R, which is rank of that particular matrix. This will be the biggest number of vectors that you need to represent all of the possible vectors in that matrix A, all right? This is how it works. So similar ideas. Now, last thing that we see here, that you can represent A very similarly, by the way, to eigenvalues. If you remember, we represented it that way, as sigma 1 times U1 times V1 transpose. And again, this probably should be Hermitian transpose here, since I'm using that Hermitian transpose everywhere here. That doesn't matter. Typically work with real matrices. Plus sigma 2 U2 V2 transpose, until you get to the last one, which is sigma R rank, okay? So pay attention what each one of these things is. This is matrix, and this is matrix, and this is matrix. All of them are matrix. When you doing, it's not dot product, okay? It's not U transpose V. It's U V transpose, which is kind of that kind of vector times that kind of vector. So it's multiplication of two vectors, which is called outer product, not inner product, and it is matrix. But this matrix has very interesting property. It has rank 1. So it's approximation of the original matrix A with some of the matrices where each one of them is rank 1. So why is that rank 1?
Because you have R, your rank is R.
No, each one of them, like U1 times V1T. Here's how it works. My claim is that you have, whatever it was, you have two vectors. You have vector E and U. False. Okay. So my claim is that this is matrix. So this is V1, V2, N, whatever, times U1, U2, which is obviously matrix. It's V1, U1, V1, U2, V1, and so on. This is the first line. Second one will be V2, U1, V2, U2, and so on. Look at that structure.
Yeah, so I think this
So
matrix.
all rows are practically proportional. Why? Because this is Z row multiplied by Z constant. Second row is same row, exactly same row multiplied by another constant. Whatever it is, doesn't matter. So all of the rows are proportional. Right? It's just multiplication by constant of the first row. So if all rows are proportional, what is the rank of that matrix? It's 1. Okay? This is how it works. So these are rank 1 approximation, and you're summing rank 1 matrices to represent any kind of matrix A. This matrix could be any rectangular matrix, right? And also it's already sorted in order of importance, which means your first sigma will be the biggest one, and last sigma will be the smallest one. Any questions on that?
So can you also say it is rank 1 because it's just a linear combination of the rows?
It's a linear combination of the rank 1 matrices. Yes. All right. And future idea that we'll be discussing, which is a very important idea, is that you can truncate it even more than that, because you don't have to use all of the tiny r's, which are like tiny last coefficients. You can squeeze it even more. You can replace sigma r by 0, and you can replace sigma r minus 1 by 0, and maybe many more sigmas by 0, which would correspond just to noise in your data somehow. So they are tiny numbers. And if they're small enough, you just can ignore them, right? So you can replace them with 0, so you'll have even shorter representation for your original matrix A. So you'll have less of this rank 1 matrices to sum up. So here's what we can do also before we get to that. We can represent these matrices in much more compact way. And this is the idea. Since a lot of things in matrix sigma will be zeros, and you multiply any kind of vectors by zeros, it still will be zeros. It will not change anything in the actual product. So what you can do something which is called economy SVD. And this economy SVD will look like that. Instead of doing m by m, if m is larger than n, okay, you can shorten it by the n. So you don't need to write the last m minus n vectors, because they will all be multiplied by 0. So in the overall multiplications, they will not even appear anywhere. They will appear just something multiplied by 0. So this matrix U times sigma times V transpose will be exactly equal to that matrix, which is not square now, okay? But it will be m by n. And since n is smaller than m, this is much smaller than the original matrix m by m. Again, if you go back, this was matrix m by m, and m is huge, let's say 1 million, okay? And n might be 2. So instead of 1 million by 1 million matrix here, and everything in that sigma matrix will be 0 multiplying all of this 1 million vectors, okay? Most of them. Here you can write that 1 million by 2. And then you're just ignoring all of the other almost million vectors, 1 million minus 2 vectors, okay? So this matrix will be very tall and thin, right? This is how this matrix will look like. So you save tons of zeros, because these vectors are irrelevant for the computation of that multiplication. You don't need them. And it will be exactly equal, all right? Now, this will be n by n, and n is much smaller, could be much smaller than m. So in that case, this matrix will be just n by n compared to the original one, which was m by n. So instead of million by 2, you get a 2 by 2, right? Which is much nicer. So practically preserving only that square here, right, by the r. You're preserving only that piece instead of taking all of the zeros in, which we just don't need them. So it becomes square matrix now, all right? And this one stays n by n, because this was n by n and n is smaller than m, so you need all of the data to be preserved. This is called economy SVD or thin SVD. You have all kinds of names for it. And the reason is that it will look like that. So instead of that original huge matrix, you'll have that thin and tall matrix. This will be square matrix, and this will be like the original matrix. Okay, this is how the shapes will look like. And they're exactly equal. So you can have just smaller dimension for each of these matrices, positive matrices at least. Okay, and this is how you do that in MATLAB. You have option which is saying economy version, all right? And then you're computing that type of matrices in MATLAB. Now, second one is compact SVD, when R is smaller or equal to minimum of M and N. So some of the columns might be dependent in your matrix, okay? It doesn't have to be all of the columns are independent or all of the rows independent. Your rank could be smaller. You could have like rank 1, all of the columns might be dependent, and so on. So in that case, what happens is you can write that M by R, which is, again, R is much smaller than each one of them would be. And then you get even smaller matrix, okay? This one will be R by R, which is even smaller square matrix. And this is R by N. Very similar to that idea, but all of them will become, these two matrices will become rectangular instead of square matrices. But you're saving a lot of memory storing them, okay? This is very important for numerical computational complexity and also memory that you need in the computer to compute all of these things, all right? So here's what happens. So when you're doing that decomposition, this is the actual meaning and actual beauty of the decomposition. That the first R columns, which is R is, again, rank of the matrix. This is column space. It's spanning the column space of original matrix A. The other ones are null space or kernel. So you get just M minus R columns here in that matrix U, just kernel space. So they all go to 0. It doesn't matter. They do not affect anything in the result. Now here you have all of the singular values. Everything else looks like zeros. And here you have row space. So first R columns of V, and this is V transpose, right? So they become rows. So first rows of V transpose are row span that subspace, all right? And the last one is null space of A, which is, well, very convenient because how you can think about that? You can think about that as these are important columns and these are not important columns. These are important rows and these are not important rows because they are not affecting anything in the matrix A. Okay? So you can think about that as noise here and something important here. Okay, so this gives you practically intuition what you can and cannot do with these things when you get into applications of SVD. Any questions on that?
Before we were talking about the input and output spaces.
Mm-hmm.
This relate to the column and row spaces?
So output is always column space. Okay, from multiplication of matrix A by any vector will give you column space of matrix A. Now you have also null space, which means matrix multiplies by vector gives you zeros. But in that case, it doesn't matter for you. Like if you get 0, it's not affecting the actual representation of matrix A, okay? You need it for completely different purposes. It's just, I'm trying, and it's not that simple as I'm saying right now. The intuition is that you need to understand from here is that farther you go to the right with these columns, less important these vectors become because you're multiplying them in the overall result by smaller and smaller number, okay? And same thing with rows here. Farther you go down these rows, and these rows are columns of matrix V, they are multiplied by smaller and smaller singular values, which means eventually their value in overall combination will be smaller and smaller. So first one will be the most dominant and important in that overall sum. Later ones will be less and less important, so you can ignore them, more or less. This is the overall idea to which I'm trying to get with that description, okay? Okay, so these are beautiful properties of SVD. It always exists, not like eigenvectors, eigenvalues. It is always there, okay? You always can find it, which is also extremely surprising. This is how it works. It has unique decomposition, which means SVD is unique for a particular given matrix A, up to sign, because again, this is simple to understand, because if you multiply U and V by -1, for example, so this will be obviously different matrices from U and V, but it still will work, right? Because it still will be U times V and minus sign will disappear. All right, so it's like up to a sign. It's unique up to a sign of each one of these matrices. Any questions on this part?
But when the up to a sign means multiplied by -1.
So no, so I'm saying that the composition is unique, which means you have unique U, unique V, and unique sigma, right? So this is like single possible solution for decomposition. You don't have like million different decompositions which all look that way. You have only one possible decomposition. But I cannot say that this is only one, because this is not completely true. Okay, this is like devil is in details, as always. And details is very simple. It's true if you ignore the sign. Okay, which means it could be -V and -U. It also will solve the problem. So you have practically two solutions, not one. So it's not unique, it's like two solutions up to a sign. All right. And as I mentioned already, the singular values could be interpreted as eigenvalues of A transpose A matrices. And we will do derivation next time. And remind you, we talked about singular values previous time, in the previous lecture. And this is one of the most interesting decompositions that we have in linear algebra. And it's pretty much universal, used in multiple different domains, multiple applications. So it's a very important thing, practically one of the most important things in linear algebra. But for some reason, most people do not learn basic linear algebra. And it's not really that much difficulty here. It's not more difficult than eigenvalues, because practically it is same thing, just for different matrices, or A transpose A, instead of regular matrix A. But this works also for non-square matrices, because A transpose A is always square, regardless of the dimensions of the original matrix A. Okay, and you have multiple different applications here, and you convert it practically into, geometrically speaking, rotation, scaling, and again rotation. So if you're looking on this matrices, U matrix is orthogonal matrix or unitary matrix, and it is rotation. And dimensional rotation, so it's kind of difficult to imagine what rotation would mean in more than third dimension. But for those two dimensions, at least you know that this is rotation. And then you have multiplication by diagonal matrix, which is sigma matrix. And this is just scaling of each one of the columns of the original vector matrix, which is built from vectors, matrix U. And then the last part, you have again rotation, because V matrix is also orthogonal matrix, unitary matrix. And this matrix is also some sort of n-dimensional rotation. All right, so we're thinking about it as rotation, scaling, and rotation again. This is the three things that you are doing by multiplying by the three matrices. And you can represent that way any possible matrix, any rectangular matrix, complex matrix, real matrix, whatever it is. Okay, so we talked about all of that. Then we said that we can represent most of it in very compact way, economical way. Depends if it is like tall matrix A or thick matrix A. We can do economy form or compact form of SVD, which means we can ignore practically most of the vectors in the matrices U and V, and most of the zeros in matrix sigma. And we can write exactly the same thing in more compact way. We'll have much smaller matrices. You don't need that much of a memory space in computer to compute a 3D. It's all much simpler if your rank is low enough of your matrix A. All right. So this was that kind of representation that you have on that slide. And then we said that since all of the columns of matrices V and U are already organized in terms of importance, because in the representations that we had, you have sigma 1, which is the biggest one, multiplied by first vector from the first matrix and second vector from the second matrix, okay, outer product. And this means that if sigma is small enough, you don't care about the multiplication, whatever that matrix is, it has tiny values. So you don't need them. You practically can ignore them. And if sigma equals to 0, obviously you can ignore them because 0 times anything is still 0. So 0 times matrix of whatever numbers is still matrix of zeros, right? So we don't care about all of these values, so we can completely ignore them and don't need even to write them. And this is what all of these compact and thin forms, canonical forms, from the simple ideas of just multiplying by 0, it's nothing. All right. And we said that it always exists. We said that you have unique decomposition up to a sign of the vectors in matrices U and V, because each one of these columns you can multiply by -1, for example, and then you'll get also the same thing because you have two matrices multiplied. If each matrix is multiplied by -1, the result is the same as multiplication of two positive matrices, right? You can multiply it. So it's up to a sign in the columns. And also it could be interpreted as eigenvalues and eigenvectors of particular correlation matrices coming from H A to the H A, which is A transpose A practically for real matrices. Okay. And I promised you to derive that today. So this is what we will do. And we will connect that to correlation matrices. So do you know what correlation matrices are? Any guess or what correlation matrix might be? So why is that matrix? I'm calling that correlation matrix A transpose A. And I will do transpose, okay? I will ignore the H because we typically do not use complex matrices. We just transpose, okay? So what is correlation between two vectors? Like standard correlation, you have two vectors. You want correlation between these two data vectors, whatever they are. What is their correlation? So first of all, you have something which is called Pearson coefficient or regular correlation, normalized correlation, where you subtract mean from each one of them and divide it by sigma, like standard deviation of each vector. And then you multiply point by point, adding that all together, you get number between -1 and 1. This is normalized correlation, Pearson coefficient. So this is statistics, basic statistics where you have Pearson coefficients. It tells you how similar the vectors are. And if it is 1, this is completely same vector because you'll get all of the values squared. But if it is -1, they are anti-correlated. If it is close to 0, then they are not correlated. They are completely different. Okay, so they're not related too much to each other, not correlated. So this is Pearson coefficient. But Pearson coefficient is based on regular correlation, which is not normalized. Pearson is normalized correlation. So what is regular correlation between two vectors?
The angle. And the angle.
It relates to angle between them, yes. But what is how do you compute it? So you have a bunch of numbers, another bunch of numbers, same number of numbers. You want to correlate that vector to another vector.
Action.
That's product.
It's just dot product. This is correlation. So dot product between two vectors is a regular correlation. You multiply them element by element and adding them all together. You get correlation. If it is positive, then you have positive trend, which means points are kind of oriented in the same direction positively, this positive slope. If it is negative, then you have negative slope, which means if one vector becoming like numbers becoming bigger, the other vector becoming smaller, okay, as you go with the elements. So it's regular correlation, okay? And that's why we call this matrix correlation matrix. On the main diagonal of that matrix, we will have variances of the vectors. And on the other things, we will have just cross correlations between pairwise vectors. Okay, this is how this matrix will look like. And let's see why. So this is not too complicated. We can just write it explicitly. And let's do that. So you have that matrix which is called A transpose A. Okay, and matrix A will be some sort of 1, A, 2, 2, A. Depends on number of columns that you have. Each one of them will be column. So, it will be rectangular matrix. It doesn't have to be square matrix specifically. Okay? Any matrix. And you're thinking about these vectors as your data vectors that you want to correlate. You want A1 with A1, A1 with A2, A1 with A3, and so on. All these possible correlations between pairwise vectors. So A1 with A1 will be variance of vector A1. Okay? So this is simple part. But this will be cross correlations. Okay? Because correlation with itself is variance. Square root of that is standard deviation of this vector. So here's what we are computing here. So let's write that explicitly. So you have that matrix transpose. So it will be A1 transpose, A2 transpose, and so on. And this will be rows now. So this is transpose of the matrix. Multiplied by A1, 1, A2, and so on columns, which is original matrix. So what do we get? It's a top left corner. You have that row times that column. First row by first column. The first row is A1 transpose, first column A1. But this is exactly dot product, okay, between A1 and A1. For the second one, you're taking first row, second column. So you get A1, A2, transpose. Again, this is dot product between A1 and A2. And so on. So you get all of these dot products. Here you get A2 transpose A2, A2 transpose A1, and so on. Right? And here you'll get it is like M by N matrix. Yeah, something like that. From generic M by N matrix. Now, obviously, this thing we will call correlation matrix. And particular element A transpose A, element IJ will be just inner product between AI and AJ. Dot product, inner product. Okay. So these are the elements of that correlation matrix. And this correlation matrix, this is what we will use. And this is why. Okay. So here is the explanation. Why singular values has anything to do with that particular matrix. So let's write a few things first of all. So A in the singular value decomposition will be U times sigma times V transpose. Right? This is what it is. Now, A transpose will be what? So we're flipping the order of these matrices and doing each one of them transpose. Okay? But what is sigma transpose? This is diagonal matrix transpose. The matrix itself, I mean, it's not changing anything in the matrix, okay? Okay, so we can write that this is V, because this is the first one, V transpose, transpose is V itself, okay? Sigma, not changing, because it's diagonal. And then you get U transpose. So this is what A transpose is. Okay, so this is just singular decomposition of regular matrix A. Okay, so we want to see how is that related to that matrix. So let's see what that matrix is here in that case, right? So A transpose A, in that case will be that thing, which is V, sigma, U transpose, and then we multiply by A, which is U, sigma, V transpose. Okay, so look at that part. The U matrix is orthogonal. What is that saying? You can practically cancel this I. Okay, so this is I, and cancel that part. So you get V sigma squared V transpose. But V transpose is V inverse. It's orthogonal in that case. Okay. So what is that thing? Look at that thing as single matrix, tilde or whatever. And you have that kind of decomposition. So here you get something like that. So from here you can write the same thing as A transpose A. And we will multiply, to get rid of that V, we will multiply by V from both sides. Okay, so we'll have V on that side. We'll have V sigma squared V transpose V. This one is also I. Okay. And pay attention, something very important to remember. Because typically we are saying V transpose V equals V transpose equals I. For square matrices that would work, but for rectangular matrices it might not. So this one is I, but V transpose might not be I. Specifically, it might not be I of particular order. Okay, but it doesn't matter. For that case, this one is fine. You just don't make mistakes. Don't assume that they are the same. Okay, because for square matrices, V transpose V has the same dimension as V transpose. But for rectangular matrices, it's completely different dimensions. Right, one might be like 5 by 5, another 5 million by 5 million. Okay, it's different matrices. So this is I, so I can cancel that part. So look well on that equation. What does it mean? How can you interpret that thing? Like, look at the first column of matrix V. What does it mean? What is that first column? So here you have, replace it with like V1 here, V1 here. What does it mean? What will be, like if you compute in that multiplication of that matrix and using only the first column, so you're taking like first row by first column, second row by first column, and you get practically first, this will be vector, right? You're taking V1, like first vector from here, multiplication by that matrix of that vector will be just vector of the same size. Okay? And this is square matrix. Is it clear why it is square matrix? Okay? So this is like n by m, m by n, so you get n by n matrix. Okay? This is m by n by m, you get n by n. Right? So if you multiply that by vector, you have some matrix, which is practically looks like that. Call it A tilde, that thing. Times V1 will be equal to what? So this is still V1 vector multiplied by sigma 1, because this is the first column in the matrix sigma 1 squared. So it will be sigma 1 squared times V1. So what is that saying? It's also the equation. This is regular equation of eigenvalues. This is a relation to eigenvalues, actually. So sigma 1 squared is eigenvalue of that matrix. And V1, which is first column of the matrix V, is eigenvector of that matrix, which is A transpose A matrix. Okay, so this is a relation. So this is matrix of eigenvectors. This is matrix of eigenvalues. Okay, which means sigma squared is practically eigenvalues of that matrix, and columns of that matrix are eigenvectors of that particular matrix. All right. Any questions on that? This is first part of relations here. We will have also other part to connect it to U matrix. Okay. Questions? Yes.
So when I was working on my project, I came across a top place matrix. Top place.
Yes.
And then I was wondering whether it has anything to do with the correlation matrix here.
It's not related. It's more of the circular matrices where you have components which kind of each row is shift of the previous row. So it's different. It's more used in
Different from the
filtering.
correlation matrix.
Complex matrices are practically describing linear systems in filtering. They are linear filters. Of linear filters. These are circular and topless matrices. Okay. But this is different kind of matrix. First of all, it's symmetrical, and topless matrices are typically not symmetrical. But this matrix is because practically this one should be exactly the same thing as this one. Okay. This matrix is symmetrical. Okay, so let's see what happens with the second part. And this is what happens to the matrix A transpose. Okay, so A transpose will be U sigma V transpose times V sigma U transpose. Again, V transpose V, you can cancel that. So this is I, identity matrix. And you get U sigma squared U transpose. Pay attention, this is exactly the same thing like here, but completely different dimensions. Because U matrix might have completely different dimensions from V matrix. One is n by n, another is m by m. Okay? But shape is the same shape. So pay attention, that number of all the sigma values will be still eigenvalues of that matrix as well. All right? Which is interesting that they have practically the same eigenvalues. But vectors in that matrix will be eigenvectors of that matrix now. So they will be called also left eigenvectors and right eigenvectors, okay? So left will be for that matrix and right will be for that matrix. Okay, so you'll have two types of eigenvalues, one for that type of matrix, another for that type of matrix. Yes.
Would they look different if you plot them between the left eigenvectors and right?
They in completely different dimensions. So obviously they are different. Columns of matrix V are very different from columns of matrix U. They have different dimension.
No. So I mean, so if you pick, let's say the first row of column, first row of the V matrix, no, first row of U matrix, and you pick first column of V matrix, would they be similar? So, and then if you find the transpose of the first row of U matrix, would they be similar? Are there any similarities?
They are not directly related in any meaningful way, at least to the best of my knowledge. Maybe there is some relation between these two, but they are talking about completely different information streams. Like if you think about that, it's like if you're thinking about SVD. Okay, let's talk about intuition here. I'm trying to think through some intuition here. The SVD in general finds some interesting patterns in columns, and this will be one of the matrices, and other matrix will tell you patterns in the rows. Let's say that example that we just mentioned about recommender system, okay? And on one end you have, for example, the columns will be songs and rows will be users, okay? That you want to predict what song you like, that kind of thing. A music recommender system, you know. So one of the matrices will describe what is common between the users, and second matrix will describe what is common between the songs. Okay, so they are, I don't want to say orthogonal information, but it's like pretty different information that they encode, each one of them.
Okay, so the reason why I am asking this is, sometimes, so for instance, you pick lights, and then you can, based on, let's say, the profile of lights of a particular pattern, they do eigen decomposition, and then represent the eigenvectors as like modes, like different modes or dimensions.
So it's like spectrum. It's like different oscillation frequency or something like that.
Yes.
This is what it is, yes. But these are singular values.
And
you have even like sigma plot, which is practically frequency plot in a sense, yes.
And then I am asking, if you don't use eigenvalue decomposition and you use singular values, how do you represent the modes, or the modes or the dimensions of the system with their corresponding singular values?
So I'm not very familiar with that particular application, so I need to think about that. I don't know the answer. So eigenvalues, again, for each singular value, you can go back to eigenvalues, but this is not direct relation. It's like through the correlation matrix, okay? So you cannot really have direct connection between them unless the matrix is symmetrical. Like if A would be symmetrical matrix, then yes, you have direct connection. But for all other matrices, which are rectangular matrices of any kind, this would not work. So there is no really direct connection that I can see that you can use. Like only for symmetrical matrices, it's very simple. You're just taking eigenvalues, making them square root of them, you get all the singular values. That's what happens with regular symmetrical matrices. Why? Because first of all of the eigenvalues of symmetrical matrix are real, not complex. So you don't have any complex eigenvalues in symmetrical matrices, which very nice property. So you can take square root of them, and they are also positive. Like for positive matrices, so you need like positive matrix, or we will talk about positive semi-definite matrices. So it needs to be positive semi-definite and needs to be symmetrical. And then everything is beautiful. You're just doing square root of eigenvalues, you get sigmas, or you're doing sigma squared, you get eigenvalues. Eigenvectors are practically the same matrix on both sides. So it works beautifully. Okay, but for other cases, it depends. It's much more complicated than, and I don't know if there is any reasonably simple relations there.
So I was just wondering, if you have a square matrix and you do eigen decomposition, and then you have eigenvectors and then eigenvalues, and then the eigenvectors, they are the let's say orthogonal dimensions, and then the eigenvectors, they are the scaling.
Yes.
Can you do that for any matrix which is not square?
That's exactly what I'm doing here, this SVD.
Yeah, but to get just,
you don't get the same matrix on left and right. So you get different matrices on left and right, decomposing it. And one matrix is telling you about patterns of the rows, and other about patterns of the columns. which is obviously carrying different type of information. They relate somehow, but not directly, really.
So if you had to make some sort of decision where you are to remove some of the dimensions to kind of filter the system, do you use the U or the V?
I will show that in a little bit.
Oh, okay.
Okay. Any other questions? So this is practically derivation of connection between correlation matrices, eigenvalues, eigenvectors, and singular values, and their corresponding matrices and how they connect to each other. These are the relations that you need to know here. Okay. Right. Let me share it back. Okay. So song recommender system. As I started to talk about, you have some sort of idea about singular values where, since they are ordered in order of importance, you can think about the first columns of matrix U and matrix V as important vectors, and other vectors are not important because you will be multiplying them by something really tiny. And you can think about that as noise. It doesn't matter. You have some noise, or you have some sort of measurement error, so you have some tolerance in your measurements. This will be all reflected in the last columns of matrices V and U. And this is why you can mostly ignore them, okay? Even if they are in the rank of your original matrix A. So this is very basic idea coming out of that understanding of how it works. It's called rank K approximation of matrix A, which means you're looking for some sort of matrix which is very similar to matrix A, but it's lower rank. Remember what rank is how many independent rows or columns you have, and this is the same thing. Rank is based on columns or rows, and they are equal, like rank based on the rows, same as rank based on the, if you have, for example, like 2 columns and 1 million rows, rank cannot be higher than 2, because all of them will be linearly dependent, all of this million minus 2, all right? So you have 2 independent columns, your rank is 2. It's the smallest one out of the dimensions, or even smaller than that if you have proportional columns or rows in some way. So the idea is we can pick that number K and to say we will just choose K most dominant singular values, biggest ones, which are at the top diagonal of the matrix sigma, okay? Everything else we will replace with zeros. Like all the other sigmas, we will just put them 0. And then we can get that compact form, which is very convenient and very easy for computations. And we will not lose much. This is the idea that if you replace that kind of thing, you save tons of memory because you have like on both dimensions, you're removing all of the zeros and so on. And you are not really losing much of a quality of your data because later columns become less and less important in representing your data, whatever it was in the matrix. Okay, so the matrix will not change that much really after you doing that kind of thing, but you can compress that matrix into something really tiny compared to the original matrix representations that you have. All right. So this is the idea that you take in that matrix M by N, and then you convert it into much, much smaller matrices. So K is definitely much smaller than N and M. You're just choosing smaller rank matrix. And you get M by K instead of M by M, okay? And here you get K by N instead of N by N. And here you get K by K instead of having that M by N. So it's like huge difference, especially if K is a very small number. K might be like 2. You're picking 2 dominant singular values. You build in that matrix based on the singular values. You get M by 2, 2 by 2 matrix, and K by 2, 2 by N matrix, which is just very small matrices compared to the original ones, original decomposition, all right? And again, pay attention that this is not always true in that case. When these matrices become not square, this is not true anymore. So this still will be, these vectors will be still orthogonal, okay? But this might not be. Okay, so we can think about that in a different way. This is different. I am trying to provide some sort of different views on what singular values give you, how it will be reflected in changes in matrix A. So you're doing that rank K approximation of the matrix A. So what will happen to the values in the matrix A? This is what we want to know. And here you have a very nice theorem by Eckert, Young, and Mirsky. Probably from 30s, 40s, I don't remember exactly, but many years ago, about 100 years ago. And the theorem states something like that if you have any kind of matrix of rank K, and we will call that matrix B, all right? So pick any matrix B which has rank K. The closest matrix in terms of Frobenius norm to the original matrix A will be that matrix B, if you're doing approximation of rank K. So here's how you formulate it mathematically. So AK, which is an approximation of rank K of original matrix A, will be argument, minimum of the argument on all possible matrices B which have rank smaller or equal to K, which is K or smaller. Like you can imagine like zero matrix or whatever matrix. Like out of all of these possible matrices up to rank K, you're picking the one that minimizes the difference. And what is the difference? The difference is just element-wise subtraction between the elements squared and sum of all of these errors. So you're practically having matrix minus another matrix, element by element, squared, and sum on that. This is what Frobenius norm is between two matrices. You're practically minimizing by that kind of approximation of the matrix. You're minimizing the distance from your given matrix to another matrix of rank K or lower. And this will be like the best matrix of rank K or lower to approximate your matrix, original matrix A. This is the overall idea, which means you will modify the elements in matrix A little bit, like tiny little bit, as minimally as possible to get to lower rank. And in lower rank, you will be able to represent it with much less effort because you'll have only a few singular values multiplied by those basis matrices, okay? And this will represent your matrix A reliably, almost precisely, okay? And this is why you can use it for compression and other tools of that kind. But in that case, you want to use it for recommender system, okay? And let's see how we actually do that. So our goal is to predict how much particular user will like particular song if they haven't ranked it before. Yes, question? On the previous one?
Yeah. So is the rank of B equal to K will produce the best result?
What will be equal to K?
The rank of B.
Will be equal to K or less.
I mean, if the rank of B is
K is you choose. It's like K means you choose how many vectors you want to use.
the rank of B is equal to K, will it produce the best result?
Again?
The rank of B matrix equals to K, same as 8 of K, will produce the best result.
So A of K will be the closest one to A. So your A is original matrix. It's rectangular matrix, original matrix. You're looking to modify a little bit the values in that matrix in such a way that it will drop the rank to K or lower, okay? So this lowest one will be that rank K approximation that we talked about, which means you're replacing all of the singular values which are small enough. Like you're keeping only K values, everything else you replace with zeros. This will be that approximation.
Because K can vary, right?
K you choose, K is constant numbers that you choose. Let's say 2.
So there might be some of the best approximation or not bad, not that good approximation.
Yes, you have million approximations. You can choose any kind of approximation of rank 2, for example, or rank whatever you want, okay? So you'll have all kinds of approximations. Any matrix is approximation of any other matrix, but some approximations are better than others, right? Some are closer to your original matrix, and some are farther from original matrix. And you need to define like in what terms, like, what do you mean by farther? So here I define that as Frobenius norm. Frobenius norm means like element-wise subtraction squared and sum on that. Okay, this is Frobenius norm. which means that elements are as close as possible and square error is the minimal between the matrices. To adding all of the square error, it's minimal for that particular approximation of the matrix, which is just removing all of the small singular values, okay, replacing them with 0. This is the best you could get out of all possible approximations. Okay, and this matrix will be of rank, whatever you choose in number of singular values. Okay, so this is the idea. So here's how you implement music recommenders. Again, you want to rank particular songs that was not ranked before by particular user, but you have some other ranks for other songs by that user and other users. So you can connect it somehow through particular matrix, okay, of rank. And again, it could be play counts, how many times you played same song, or it could be that you're giving stars to that song. It could be all kind of ways of ranking songs. It doesn't matter in that case. So here I'm using just number of stars, for example, from 1 to 5. So each user can rank whatever song from 1 to 5, as you have in all kind of recommender systems now. And then based on that, it will understand like what you like and what you dislike. And then we'll recommend something that's similar to you users also like or dislike. So it will understand that part. All right, so let's see a simple example here. So rows will be users. So we'll define that matrix of rating as R. Rows will be users. You have 5 users here, and you have 4 songs. Simple, small example, okay? But in practice, you can have like millions of users and billions of songs, whatever, okay? So we will work with 4 songs and 5 users. 0 will mean unrated. So they never heard that song, never rated it. All right, so we don't know. And we will want to pick some of those zeros and replace them by our best guess if this user will like that song or they will not like that song based on what they ranked before. And here is that network of connectivity to different songs. I have only 3 users, but you have like 2 more below. So first user will be ranking song 1 as 5, song 2 as 3, and song 4 as 1, and unranked song 3. So we don't know, never heard it, okay? User 2 will have, again, 4 and 1 for the first song and last song, okay? And never rated 2 other songs, and so on. So each user has their own ratings. Some of it is missing. You want to complete that matrix somehow. Is it clear what we are trying to do? Okay. So we want to approximate that matrix with singular value decomposition first. Okay, so we'll have that matrix, and we will pick particular rank, which will be only 2 features. Like rank will be 2. Obviously, rank here will be most likely 4, right? This is rank of that matrix, so original matrix R, but we want to choose only 2 features out of 4. We will say like 2 other features are not important for us. We will pick 2 most important features. So U will be user features and V will be song features. Okay, one is for rows, one is for columns. And this will somehow magically extract all these patterns which are hidden, and we don't know these patterns really, almost like deep learning. And SVD is used in deep learning, multiple different things. So it extracts some pattern when you're thinking about user, for example. Some might prefer like energetic songs or acoustic music or some other property which we cannot really get from the table, right? It's not something the table is telling us really directly, but just by clustering, when you have the table huge enough, like for small tables, it will not really extract anything useful. But for huge table, when you listen to millions of songs, that would work perfectly because it will pick the exact properties and what is important to you, what is not important to you. It will automatically do all of that using the decomposition, all right? So this is the beauty of that thing. So I'm just computing SVD on that particular matrix and picking only the first 2 columns of matrix U and 2 columns of matrix V, like rank 2. This is what I decided to use, only 2 features. And then this matrix will be 2 by 2 with 2 features. Most likely you have 2 more here, which are smaller than 6. They have to. be smaller than 6 because it's ordered already, organized in order of importance. But these are the matrices that I get in that rank 2 approximation. Now, to predict, for example, what user 2, how much they will like song 3, and like pay attention, that user 2 haven't ranked song 3 here, right? But they ranked song number 1, which they liked, and song number 4, which they disliked, right? This is what we know about that. So what else we know about song 3? We know that user number 5 ranked that as 5, like really loved it. But they also loved the song number 4, which our original user hated, okay? Which means that the taste of the user 5 most likely should be opposite from the taste of user 2, okay? And most likely they will dislike that song. This is kind of intuition, but now we want to prove that intuition using SVD, okay? And again, for like million by million table, you would not be able to do that kind of intuition. This is like only for small tables, you can kind of think like, can I approximate and can I guess what would be the answer? And this is the answer because like the taste is opposite for that user. Okay, so this is what you'll get. You multiplying practically that second row of the matrix U, which is 1 by 2, like a regular vector, multiplying by that sigma, which is given here, multiplying by third column of V transpose, and you get all of these numbers. Your ranking is negative, which is like horrible. User hates it. Okay, so higher means better, right? So predicted rating was like less than 0, so user 2 very much likely will hate that song, will not enjoy it. Okay, this is how you approximate it. So if it is high number, close to 5, then it's strongly recommended. If it is low number, just don't recommend it. This is how recommender systems work, all right? And here is a full table, which means all of the missing values that we had before. If you just to remind you what was missing, almost all of the column number 3 was missing, and here some zeros were missing, here some zeros were missing. So we completed them, and you get from the original matrix, like all of the blue ones are missing, okay? We replace them with our ranking here. So actually, this user will like that song, and this user will most likely like the song like 3 out of 5 approximately. And this user will hate that song, which is, as you can see, negative 0.46. And this user also will hate that song, most likely, okay? And other songs, it will be fine, practically like 2, about 2 for these users, which was missing here. So you actually can complement that entire matrix with values of how likely the user will like the songs. But you can do many other things with the same recommender system. Let's say you can reconstruct brain connectivity matrices with the same thing. Would that work? This is an interesting question, actually. What are the assumptions for your matrices that it would work? Like what assumptions on the brain connections you need to make for that system to be useful for brain connectivity? Let's say you're missing some values in connectivity matrix. You know that different parts of the brain talk to each other, and you have some correlations between signals coming from different places in the brain. And you're saying, well, I cannot measure some of these connections, but I can measure some other connections. Is there any kind of connection which is more important than some other connections? Can we rank them by importance? This is an interesting question that would work for the brain, for example, like connectivity in the brain. So sometimes you can think about problems that would be solved by that type of approach, and sometimes you just cannot think of any rankings that you would associate with particular connections. Do you care about strong connections versus weak connections? It's also important, right? And this is similar to ranking in that case. And just to show you basic MATLAB code, by the way, any questions on like how it works? It's relatively simple. You just taking particular row and column in the SVD, and then this is your importance, practically speaking. So this is the code which is doing that. So you're starting with defining that matrix R, doing SVD of that matrix R, Then you're saying I have only k equals to 2, which means I will pick only 2 features. And then you're taking from 1 to k, which means all of the column, but only first 2 column. Yes, so all of the rows, which means you're taking like from top to bottom, everything. And then from left to right, you're taking only the first key, from 1 to k columns of the matrix. And same thing for the V matrix, okay? And this matrix is k by k matrix. So you're taking first k by k matrix corner of the matrix sigma. We'll call it sk, because we don't have sigma, unfortunately, in MATLAB. So you're displaying all of these matrices, and they are displayed here. This is what you've seen on the previous page, same numbers, practically speaking. And then you're saying, let's say you have user 2 and you have song 3. So predicted rating will be that value from that predicted matrix R hat, okay, which will be just element in that matrix here. All right, this is how you predict it. And then we just plot these matrices like that. Any questions on that? Okay. So let's see image compression. Practically speaking, nobody is using SVD for image compression anymore. But they have much better methods for that, like JPEG 2000. So it's already for 25 years we have that method, which is compressing images much better than this method that I will show here. But it's just for showing you how you actually can compress data by a lot. So JPEG is not lossless, which means you lose some information when you are doing JPEG compression of images. You're familiar with JPEG, right? .jpeg image. You have PNG, you have JPEG, you have GIF, you have BMP, which is uncompressed, huge image for the same thing. But JPEG is losing some information from the image. So it's modifying the image a little bit that it will not be visually different. So you will not notice it if you're not getting like compression of very high ratio. JPEG image looks almost like the original image. And it's like probably like 1,000 times smaller than the original image if you're looking on the amount of data. Because that standard is looking of how we see stuff. Like it's based on our eyes, actually, like what we ignore and what we actually pay attention to. So this is JPEG standard. But this is much simpler than that. It's just based on rank K approximation of images, okay? So let's say you have image compression used on SVD and you have that original image in that corner here, okay? This is original image. The image has a resolution of almost 3,000 pixels squared, approximately. About 3,000 by 3,000. It's not exactly rectangular, not exactly square, it's rectangular. So one is 3,000 something, and other dimension width is just 2,975, whatever, okay? So it's big image, big resolution image. And what we are trying to do here, first of all, we're reading that image, converting it into black and white, gray level. Okay, this is what that command is doing, RGB to gray of that read of that particular PNG image, which is lossless compression. It's not losing any information. And you're plotting that in the first subplot here. So this is the original image. Okay, so far. Then you compute SVD of that image in already econom state, economical representation. So you're removing all of the singular values which are zeros. Okay, so your matrix has become kind of smaller in that case. But we want to compress it with different kind of ranks. And we will pick rank 10, rank 30, and rank 100. And as you see, the original rank was about 3,000, much bigger, okay? So I'm picking like 10 dominant singular values first, okay? Just to see, is it enough or not enough? So I compressed image will be that U of from 1 to R. So I'm picking the first R columns of matrix U, first columns are columns of matrix V, and R by R matrix S, which will be like 10 by 10 matrix, okay? So I will plot that result now as I compressed, and this will be image like that. Okay, this is 10 dominant singular values will represent that image as a blurry stuff. Okay, you still can recognize some shape, right? You can recognize some things, but it's not great to eye, right? Just visually not very great in terms of compression. So 10 is not enough, clearly. So let's try the same thing. This is exactly the same code, just R equals to 30. You'll get already something much better, still a little bit blurry here and there. You can live with that. You can see the image. It's not as clear as this one, but it's fine. And I'm using only 30 by 30 matrix instead of 3000 by 3000, which means I removed the dimensionality by 100 squared, okay, times, which is a lot, 10,000 difference, all right? And then I'm trying R equals to 100, which practically constructs pretty well the entire image. Okay, so I'm taking only 100 out of 3000, and they are reliably, this basis of 100 images reconstructs back reliably my image. And all of these original basis images are rank 100. Okay, so I'm adding its linear combination of images, and each image is rank 100. All right, this is what SVD does. So if you're thinking about compression of that thing, the original image uncompressed, completely uncompressed, okay, would be like 10 megabytes close. It's 10 million bytes, which is not exactly 10 megabytes. Do you know the difference between megabytes and millions of bytes, which is different? Not by much, but different. Because we are using all of these bytes, it's in binary system. And 1K is 1024. It's not 1000. So this difference of 24, it is different, okay? It's not the same as thousands. It's not like kilobyte is not 1000 byte. It's not counted in thousands, it's counted in 1024, okay? Because it's 2 to the power of something. Okay, so it's powers of 2, and we approximate it by powers of 2, and since it's approximated by power of 2, megabyte is not like 1 million. It's different, close, but not 1 million, all right? It's just power of 2, which is closer. So this is 10 million bytes, 10.4 million bytes, okay? Now, and when you're doing rank 10, you get about 65,000 bytes, which is much smaller than that, okay? Like way smaller than that. We are talking about more than 1,000 difference between K, like it's difference of 1,000 between K and M. Now, with rank 30, you have 194K, and with rank 100, you get 648K. So again, if you would look at image of that kind of resolution and having like almost half a megabyte for that image, you would say, this is black and white, right? It's not even color. So say it's not great compression, but compared to the original one, it's a lot. Okay, compared to 10 million, 600 compared K compared to 10 million, it's a lot, all right? So you can use it for compression of data if you want to. Another thing that you want to look at is called sigma plot. And this is plot of singular values. And it's always a good idea to plot that kind of plot. It's just plot as a function of R. And R is that rank which is going higher and higher. Eventually you'll get just zeros. But in that case, this will be 10 to the negative 2. This is the smallest singular values that you get in that matrix. It's probably 2975th. Will be somewhere here at the corner. And the first one will be here, which is like orders of magnitude. It's higher than 1000. Okay, so the first one is higher than 1000. The last one is less than 0.01 or something like that. Okay, so a huge difference between them. So you can plot it even on logarithmic scale. As you see, I plotted that on logarithmic scale. So it's semi-log function in MATLAB to plot that on logarithmic scale, like that. So this is what plots that thing. And these are just diagonal values of the matrix S, all right? People also call that spectral representation. Again, if you remember eigenvalues, we call them spectrum. Same thing for singular values. There's a spectrum, like how it responds to particular R, rank-based spectrum. Any questions on that? Now, why do we need that plot? We can identify that point where it starts to be very flat, okay? And this is a number of singular values that you need to pick for your rank. So probably a few hundreds should be more than enough, because after a few hundreds, it gets pretty flat and not changing by much anymore, okay? It's not contributing anything to your image. Okay, and last example, any questions on that? Last example is eigenfaces, and eigenfaces, what we have here is representation of images with less images of the same kind, basis images. I mentioned that some time ago as application for eigenvectors and eigenvalues. You can do the same thing with singular values, singular vectors. The idea is that you're making, from each image, you're making one long vector, column by column, like making it one long vector, and you put them in the matrix A, and then you're doing just a 3D decomposition, and you're finding rank K approximation, let's say like 4, K equals to 4. So you're picking 4 images which you can organize them back from the vector to image, because you know the dimensions, right? You can put it back, most important vectors in V, and they will look most likely something like that, okay? It's still face-like looking, but not exactly faces. But these are highlighting the most important components of the faces, which are edges mostly and darker places versus brighter places in the face. So it kind of picks all these features automatically somehow using SVD, which are the most important to represent most of the faces in the database, okay? So you'll have that basis, and you'll be able to write completely new image, like new face that never seen before, okay? As linear combination of all of these basis functions, eigenfaces, okay? And this will be low rank eigenfaces, like rank 4 images, okay? And then you just find all of these coefficients, and then you write new image as simple as this linear combination of 4 other images. So it's reconstructed practically just from that vector that you have here, all right? This is the idea of eigenfaces and why people do not use it anymore. First of all, because you have deep learning, which is doing that much better now. And second, it's kind of sensitive if you move the image a little bit, and it's difficult to catch exactly the image at the same position. So you need face to be very aligned, that you'll be able to find all of the common features for faces. And you need kind of to stretch it and to squeeze it to match different sizes and shapes of the, so it has additional difficulties. I'm not getting into that. It's just idea that this was one of the most popular methods for recognition of faces before deep learning, okay? People used eigenfaces to recognize faces for security reasons and other reasons, all right?